All right, so have you ever really stopped and wondered how an AI actually learns? I mean, not the sci-fi stuff, but what's actually happening under the hood that lets a computer get better at things? Today, we're going to peel back that layer and look at one of the absolute cornerstones of modern artificial intelligence.
I mean, seriously, think about it for a second. When a self-driving car gets something wrong, or a chatbot gives you a bizarre response, it's making a mistake. But the magic is that it can learn from that mistake so it doesn't do it again. The real question is, how on earth does it do that?
Okay, to get our heads around this, we're going to start with something super simple, a little guessing game, really. And by seeing how a machine figures this out, we're going to uncover the fundamental secret of how they learn.
So here's the challenge. We've got two little points on a graph. The computer's one and only job is to find the perfect straight line that cuts through both of them. Remember our old friend from math class, y equals mx plus b? Yeah, the computer just needs to figure out the right m and the right b. Simple enough, right?
Now, the machine has absolutely no idea where to even begin, so just like you would on a test you didn't study for, it just takes a wild random guess. Let's just say it pulls these numbers out of thin air. M is -1 and B is 5.
So how did our random guess do? Well, let's look at the damage. For that first point, where x is 1, our line predicted a 4, but the real answer was 3. So that's a miss. For the second point, where x is 2, it predicted 3, but the real answer was 5. Oof, another miss. Now to figure out just how wrong we are, we measure that error and square it. That gets rid of any pesky negative signs and tells us just how far off we were.
And if we average out those squared errors, we land on this number, 2.5. This is what's called the mean squared error, or MSE. You can just think of it like a golf score. It's one number that sums up how bad our guess was. And just like in golf, you want that number to be as low as humanly or machinely possible.
Okay, so we've got a score, and it's not great. How do we make a smarter guess next time? How do we find a system to get that error number down? Well, to understand this, we need a really powerful metaphor.
I want you to imagine that every single possible guess for M and B exists somewhere on this massive invisible landscape. And the height, or the altitude, at any point on this landscape is the error score for that guess. So really high mountains are terrible guesses with lots of error, and these deep, low valleys are great guesses with very little error.
Now this landscape actually has a formal name. It's called a loss function. You can think of it as just a map that mathematically tells you how costly or how wrong any particular guess is. And our entire mission is dead simple. Find the absolute lowest point in the deepest valley on this map.
And that leads us to the million-dollar question. If you're standing somewhere on this giant, foggy landscape and you can't see the whole map, how do you find the bottom? All you know is your current altitude. What's the plan? The answer is a beautifully simple algorithm called gradient descent. And it's so cool because at every single step, it gives us two magic numbers that tell us exactly what to do next. Okay, the first magic number is the gradient. It's a little bit of calculus that basically acts like a compass needle that always points in the direction of the steepest way downhill from where you're standing. The second number is the learning rate. This one's on us, we pick it. And it just tells us how big of a step to take in that downhill direction. Are we taking a tiny little baby step or a huge running leap? And this right here, this is the whole engine of learning laid bare. It's just a loop. You figure out your error, you find out which way is downhill, you take a little step in that direction, and then you do it all over again, and again, and again. And with every single step, you get a little bit lower in that valley of error, and your guesses get a little bit better. It's that simple. Now, just like there's more than one way to hike down a real mountain, there are a few different strategies the machine can use to take these steps. Let's quickly look at the three big ones.
So one way is to look at all of your data to find the absolute perfect downhill direction before taking a single confident step. That's called batch gradient descent. It's accurate, but it's painfully slow. On the other extreme, you could just look at one random data point, take a quick guess of a step, and then another. That's stochastic gradient descent. It's super fast, but the path down is really erratic and zigzags all over the place. And that's why, for most AI today, the winner is mini-batch. It's the perfect middle ground. It looks at a small batch of data, gets a pretty good sense of direction, and gives you a great mix of speed and stability.
Okay, so our model is getting really good at finding the bottom of the valley for our two little data points. But this brings up a much deeper and way more important question in machine learning. You see, the real goal isn't for the model to just get good at navigating this one specific valley we've shown it. The goal is for it to understand the general shape of the landscape itself, so that if we drop it into a brand new valley it's never seen, it still has the skills to find its way down.
And the way we do this is we split up our data. We give the model the training data. This is like its practice map. It uses this map to learn the path down. But then we hit it with the validation data, a totally new map it has never ever seen before. This is the final exam. And if it does well on this map, then we know it has actually learned how to navigate, not just memorized a single route.
So, the crucial point is avoiding this massive trap called overfitting. This is what happens when a model aces all the practice tests, but then completely bombs the final exam. It got so good at the specific twists and turns of the training map that it's useless on any other terrain. It's the classic sign of memorization, not real learning.
And that really brings us to the big picture here. This incredibly simple idea of just taking steps downhill isn't some niche algorithm. Gradient descent, in all its flavors, is the fundamental engine that drives learning in almost everything we call AI today, from the massive language models to the camera on your phone.
The source material just puts it perfectly. The whole game is to minimize that error, that loss, by tweaking the model settings over and over again. It's just a process of trial, error, and slow, gradual correction, but repeated millions or even billions of times.
So I'll just leave you with this thought to chew on. If this one simple, elegant idea, just taking small, smart steps downhill, powers so much of our incredible modern world, what other huge, seemingly impossible problems could we solve just by breaking them down into a simple loop of guess, measure, and adjust? Thanks for tuning in.